Hello everybody, and this video is going to be all about circles and about how to draw circles in a bitmap. Now there's a few ways of going about it, and I wanted to cover, basically give a quick survey of different approaches and different pros and cons of each. And we'll start with kind of a naive, very simple way of thinking about it, and then we'll see some more elegant and more efficient way of doing it. So what is a circle? Obviously it's a two-dimensional shape. You can say it's an infinite set of points. That's true for any shape. And we can say that it's all the points that are of equal distance from some other point. It's kind of a convoluted way. Let's be a bit more formal. So say we have some point in two-dimensional space, and we have some measure of distance. We call it r. And we say that all the points in that two-dimensional space that C is a part of that have this distance that we were giving R from that point C form a circle. Now notice what isn't said in this way of defining it. There's no functions, there's no equations, there's no notion of radius or circumference, or there's no pi, there's no angles, there's no radians, there's no degrees, none of that. All of these things are not part of what a circle is. There are mathematical tools to analyze and work with circles in a particular domain, algebraically. So there's this distinction between what's the tool that's not part of what the definition of a circle is, and what's the actual definition. This definition comes from the third postulate of Euclid, and it holds for even non-Euclidean space, like on the surface of a sphere, which is two-dimensional, but it's non-Euclidean. So it's very general, and it's really the only thing that you actually need to represent a circle and draw it. Okay, so can we draw a circle with a computer? That's what we're interested in. So the bad news is that not really, because well, the 2D space that we were talking about is the continua, and our pixel grid in our bitmap or our frame buffer is a discrete space. But we can get close. We can do some approximation of a circle. So we're not actually drawing a circle, because that's not possible. What we are drawing is an approximation of a circle that fits in our two-dimensional grid of pixels. Okay. So how can we draw an approximation? So there's a few ways of going about it. So we can use angles in trigonometry. We can use something called the rational parameterization of a circle, and we'll go about that. It's less well known. It's less being taught less often. And we can use the Pythagorean Theorem in some way, in a few ways actually, that we'll cover. But that's the main thing that we'll cover eventually. Okay, so let's talk about trigonometry. So say we have this plane, two-dimensional space, and we have this point on it, and we have this measure of distance, and that's all we need to form a circle, basically. Let's start with assuming that our point is at the center of the world, the origin of the two-dimensional space, and that our measure distance is 1. That forms what's called a unit circle. And if we aim at starting from the origin, which is our center point, aiming at the angle theta, and we walk along 1 unit, we end up at a point which is on the circle. And that point has coordinates, as you're familiar with the trigonometry. So the x coordinate is going to be cosine of this theta angle, and the y coordinate is going to be the sine. Okay, so what if we don't want to do a unit circle, what we want any kind of measure of distance, well, then we just multiply this, because this cosine and sine are a fraction between 0 and 1, and we're just going to scale up the our point away from the origin. But what if we want some other point that's not in the origin? Well, we'll just add the coordinates of that point to whatever we get, and that's true whatever the point is. Okay, so say we want to draw it using this scheme, so we can start with the theta angle of 0 degrees, and we can walk along our distance to the right, and we can draw a pixel there. And then we just increment the theta by some constant increment and evaluate the two expressions at the top right, and we get an x and y. These are going to be fraction like real numbers, and we're going to need to discretize them to integers. That's part of the approximation process, because we need coordinates on our bitmap, which is integer, because it's discrete. What you will notice is that the choice of step of angle that we're stepping through is going to be dependent on the distance, the radius. You're going to need more subdivision for larger circles, obviously. So that's something to keep in mind when doing that. But anyway, so we have our starting point, and we can just increment the each step of our constant increment of angle theta, and just reevaluate all these two expressions, and then discretize it to a coordinate on our bitmap, and we put a pixel there. We can go over 360 degrees, and we have a circle. Okay, another way is using the rational parameterization of unit circle. So a lot of people are not familiar with that. It turns out you can get any point on a circle, almost any point on a circle, using without any square roots and without any trigonometric functions. So we have a point on the origin here, and we have some point that we choose along the y-axis. It could be anywhere on the y-axis. Then we have this point on the left, which is at x minus 1, and we imagine a line that goes through those 2 points, and it will intersect the circle at a specific point. And then we have a point on a circle, so we can just slide this thing along this point that we have along the y-axis, and we can have our circle. So this is the parameterization. As you can see, it's a little bit more complicated than the trigonometric functions, at least on the surface of it. The trigonometric function is way more complicated than this if you actually go into it, but anyway, so this is the parameterization. We have our t value, which is the measure along the y-axis of our teal point there. So we still have just one parameter, just like we had with the angle. So we can just slide it around, and we get the same thing. And obviously we need to multiply by r to scale it whatever we're getting. And also at the center point to get it out of the origin. So there is two caveats that you should be aware if you ever try to do that. So say we have this uniformly spaced points along the y-axis that for the step side that we have chosen, and then we do this kind of projection thing with the parameterization form that we just saw, and we hit points on the circle. And if you notice, even though the points that we started with were uniformly spaced, the points that we get on the circle are not. and I'll just highlight that with this colorization. So they're more kind of spread out along the center there, and they get a bit more concentrated as we get to the top. So that's one thing to keep in mind. There's ways around this. Another thing to keep in mind is that we can do this thing, but as long as once we pass this threshold, we start going very quickly off into infinity along the y-axis. So one way to circumvent that is to just draw the right circle and then flip the scheme. Basically, invert the result we're getting. To draw the left side of the circle. Okay, and then we have the Pythagorean theorem. So say we have some point, any point on the circle. It's going to form a right triangle as its components, and we know that the Pythagorean theorem will denote the relation between the coordinates of that point and the measure of distance r that we have. But notice this is a relation, it's not a mathematical function. Reason being is that for each single input there are potentially two outputs, and that kind of violates the criteria for what a function is. Function can only have one output per input. So if we define our input as x, we'll see that y is going to get us 2 points, two solutions. And if we choose y to be our input, then still we have two outputs. So we can't just plot it with numbers and expect an answer in a usual way. So, but we can still use that relation. So say we have a pixel coordinate in our bitmap, and we want to know if it's on the circle or not. Well, we can take we know where our coordinate is in terms of our bitmap, and we know where our center point is on our bitmap. So we can just take the delta of that and we get our x measurement for the coordinates of a potential point on the circle in the space of the center point as the origin. And we can do the same for y. We can just take the delta, and this will also work on the other side. The deltas will be negative, and then will be increment, and we'll extend it beyond the center point. Okay, so we have this scheme. Let's say we start with the position that's on the center, and then we take we go left by r distance, and then we go up by r distance. So we start off at the top left corner of where our circle is going to be. And we can do this delta thing to get a y measurement. In this case, the delta is going to be 0, so y is going to be r. And so we get the y and we get the x, like we said, and we can then calculate what the potential r would be for this particular pixel. And then we can compare this against what we expect it to be if it were on the circle, just taking the square root of the sum of the squares and compare to our r. And we can just do that, incrementing our pixel, and for each pixel just derive the coordinates in the space of the circle in its local coordinate space for its center, and just do that for each pixel from -r to r, basically scanning through. And then we go to the next row, and here the delta is not going to be 0, and it's still going to work, and the square root again is going to give us some real number, so we're going to need to discretize it in some form, and then compare it to the r that we expect, and then we get a circle approximation like that. Okay, let's see how how this looks in pseudocode. So we just loop in y from -r to r, take the square root, take the square, and then we do the same for x, and then we take the square root of the sum of squares and compare it to r. And now we need to know where to draw our pixel, if it is equal, so we know that we are on the circle. So we have our point on the bitmap, and it's and we know where our what our x is that we're looping, because we're looping, as you can see, in the coordinate space of the circle with the center as its origin. So we need to map this back basically to our bitmap coordinates, so we know where to put a pixel. We basically do the inverse mapping of what we just saw. So we use the delta and we get the x, and that's going to be the x in the coordinate space of the bitmap. We do the same for y, take the delta, and then we have the y. And then we just scan through left to right for each pixel, and then after a while we just get the entire approximation and we have our circle. Now, so far all our approaches that we covered are kind of the naive way of approaching the problem, because it turns out that the circle is extremely symmetrical. It's actually the most symmetrical shape we know. So we can capitalize on that. So if we have a circle and its approximation, we can just slice it, say on the x-axis, and then we see that the pixels that represent it in the approximation are basically the same at the top and the bottom. So we can just compute just the top part and just mirror it to the bottom. But as we can see, it's the same thing on the vertical axis, so we can do the same there. So we can actually just compute the quarter of the circle and mirror where the pixel coordinates are, both vertical and horizontal. But we can go even further than that and split it 8 ways, and in this way we're gonna be just doing this 8th pizza slice there, and then we mirror within each quarter of the circle. We can mirror the 8th that we did around that diagonal, and that's actually very, very simple. There's no math actually. It's just substituting x for y and y for x in each corner, in its quarter, and then we basically do a lot of mirroring and substitution, and we can actually get away with just doing the 1/8 of a circle in terms of the computation, and the rest of it is just going to be mirroring around 8 times basically. So say we choose the red part for the thing that we are computing, and we're going to see that whatever we are getting, we can just use the values and copy it over to another set of coordinates, and just stick a minus sign on the y there, and do the same for the x, for the vertical mirroring, and obviously the x and the y with both minus. And then we need to take care of the mirroring. So mirroring is just substitute this is exactly the same coordinate, just anytime you wrote an x, you're going to be writing a y, and every time you need to write a y, you're going to write an x. Otherwise it's exactly the same. So we just do this cross flipping, and we do that for each of those. So we do that for that thing and the rest of them. Okay, so we end up just computing the red part, and every result that we get, we just kind of broadcast the x and y values that we get to all 8 combinations. So these are 8 combinations of plus and minus for x and y, so that's 4, and then another 4 for when we flip between x and y. So we just get 8 ways, and then we draw our circle like that. We just computing 1/8 of it. And when do we stop? When will we stop? Once we hit the 45 degrees angle diagonal, which is exactly when y starts being greater than x. That's the only thing that we need to check for. Okay, so let's see how that goes. So just zooming in on the scheme here. So we have our point, and we start off, say, at the right. So we have our measure of distance r, and we can start off with the point plus r to the right for the x, and we start with whatever the point is for the y, so 0 delta, and then we have another set of x and y's for the coordinates in the space of the circle itself. So we're starting at x equals r and y equals 0. And then we check all the time that we haven't gone through the diagonal where y ends up being greater than x. So as long as y is less than or equal to x, then we're good. And what we do is just increment our pixel by 1 pixel at each iteration. So and then at each iteration we also check that we're still on the circle. So we just take the x and y that we already have and generate the hypotenuse of whatever we get, and we compare it against r squared. Notice that because we're only using that to test if we're on the circles or not, but not to an actual taking the actual measurement, the actual value that we get, and we can get away without having to take a square root. So it's just taking the square and comparing. And if it is less than or equal to r, if we're still roughly on the circle, then we put a pixel there, and we increment our y's to be going up. And then we ask the question again, are we still on the circle? And this time we'll get no, because the hypotenuse ended up being a bit larger than r, at which case we just move 1 pixel to the left. So we do that and update our coordinates, and then we ask the question again, and then this time we are on the circle. So we put a pixel there, and then we go up and we ask the question again. Yes, we're still on the circle, and then go up, and yes, we're still on the circle, and then another one, and now we're not on the circle. So we take 1 step to the left, decrementing x. So as you can see, y is going up and x is going down up until y is going to be greater than x at some point. So so now we go in again, and now it is on the circle. So we put a pixel, then we increment, and now it isn't, so we have to do another step and put this another one, and eventually we hit where our y has gone beyond our x, and we are done. Let's quickly have a look at some pseudocode. So we have a draw circle again with the C and R in the color. We'll initialize x and y for r and 0. We'll pre-compute r squared because we're going to be using it a lot. And then while y is less than or equal to x, we'll draw our 8 pixels, which is just our C center point plus and minus the x's and y's with all 8 combinations as we saw. And then we're gonna do the check if in this case I did the opposite, just checking if we went past the circle, we got off the rail, then we just decrement x, and regardless of what happens, we increment y, and that's it. This is how we draw circles. Hope you enjoyed this video. Hit the like button if you liked it, and if you want to be notified for further videos like this, you can subscribe to the channel. That's it. Thanks.